Have you ever wondered how we can harness the power of radioactive elements to tackle our growing energy needs? In the quest for alternative energy solutions, we find ourselves looking at concepts such as thermionic emissions and the use of radioactive materials like thorium and cobalt-60. Let's dive into the fascinating world of thermionic emissions first. This phenomenon involves the emission of electrons from a heated metal or a metal semiconductor. It's based on Richardson's law, or the Richardson-Dushman equation, which was first published by Owen Williams Richardson in 1901. According to this law, the emitted current density is related to temperature. The equation reveals that the current increases rapidly with temperature when it's less than the work function of the metal. At higher temperatures, the increase is quadratic. So, how does this relate to thorium and cobalt-60? Well, thorium is a metal and cobalt-60 is a radioactive isotope of cobalt. When applied to the cathode of a magnetron in an electric generator, these materials could potentially enhance the thermionic emissions, thus increasing the energy output. The high-energy electron beta ray energy from the cobalt-60 could be converted into electricity. However, there's a hitch. The devices would become too hot to operate and could potentially melt. This is where the concept of operating in a cryonic vacuum-cooled vacuum tube comes into play. By maintaining the devices in such an environment, the excessive heat could potentially be managed. But this is all theoretical. The practical application of these concepts needs further exploration and development. Funding and research are necessary to turn these ideas into reality. To summarize, we've explored the concept of thermionic emissions and its relation to temperature. We've discussed how radioactive materials like thorium and cobalt-60 could potentially enhance the energy output of electric generators by increasing thermionic emissions. However, the practical application of these theories presents challenges, including the management of excessive heat. Despite these hurdles, the potential benefits of this approach make it a compelling area for further research and development. This exploration into the potential of thermionic emissions and radioactive materials for energy generation underscores the need for innovation and research in our quest for alternative energy sources. The future of energy may well lie in the heart of these radioactive elements waiting to be harnessed.